Everybody, just testing stream here. Hey everybody, currently we have some thunderstorms here. So let's see what we can see, right? We have a trough here, visible in the 500 millibar height lines. Upper airflow is moving like this. There's a lot of PVA in this region. And as this troughs move to the east, this convective region will also be pushed more to the east. So currently we have some thunderstorms in the north of France. So let's see what we can see, right? I'll just turn off the storm tracking for a minute. So as you can see here, hey, live on Tropics. Just trying to do a stream here. Don't kill me if it's bad or I've never done this before. I hope you can hear me because I have no idea. If you can hear me, just shout. I'm just trying to see here what we can see. Yeah, it's I've put it on extremely low, but I have no idea if this works or not. I was just with the convective season going on, I thought, okay, let's just do a stream and see how I can do this. Oh, yeah, I have no idea how the performance is because as I already mentioned, I've never done this. There's a bot running also, um, but I have no idea if this works or not. So actually, what we can see here is we have some thunderstorms here. Not too much to talk about, um, and you can see there was a split here for a minute, but now the thunderstorm is moving in that direction. What you can also see is actually, and it's quite cool, like uh, like this one here, you could see like a sort of gust front moving in that direction. You could see it here. Also nice to see. And I was wondering what that gust front would do to these thunderstorms here. I was kind of curious. And also, as you can see, just to give you a sit rep live on Tropics, you're my only viewer now. As you can see here, there's a trough here in the 500 millibar height lines. Upper level airflow is moving like this. You can see that the spacing between the contours is shorter than it's here and here, meaning that there's a lot of PVA in that region. And you can see that also if we go to if we go, for example, to our weather charts. I have some weather charts available, which I also created. You can see that actually. So let me move to my weather charts. If I switch this one to the other one, I hope I can find it. Yes. I should be able to find it. Hang on. I think it's this one. No, it's not this one. It should be that one. And it is that one. Let me go here. I'll show you. As you can see here, um, I have here the GFS and the geopotential height tendency. And if I rock this thing back and forth, you can see actually red is upper level motion, blue is sinking motion behind the trough. And as you can see, the geopotential height tendency is turning red, meaning geopotential height is lowering, meaning that the upper level forcing downstream of the trough, downstream meaning here, where's my mouse? Downstream meaning here, this is the trough, this is downstream, this is upstream. As you can see, sinking motion here, rising motion here, and this gives rise to the thunderstorms. All right. I don't know if you know, you can't see what I draw apparently. That's kind of bummer. You can't see what I draw. Oh, now you no, no. Yeah, now you can see what I draw. So actually here, downstream of the trough here, you have this upper level motion. Blue here is the sinking motion. You can see the same thing actually here in the QG omega, which is even more pronounced. You can see the upper level motion here and the sinking motion here, right? If I rock this back and forth, you'll see what I mean. If you rock this back and forth, you will see that as the trough moves eastward, the upper level motion will also move eastward. And if we look at the precipitation, actually, as the trough moves eastward, look what's happening to the precipitation field. It would invigorate, as you can see, because the trough here. Oh, again, same thing. Let me erase these things. Here, trough. Look at the spacing. And look at the spacing here. So there's a lot of PVA here leading to vertical motion, leading to invigoration of this precipitation field. Eventually. So I thought, okay, let's just do a stream and potentially, follow this situation a bit. Let me go back here to the ChaseBuddy. Sorry, I didn't see what you wrote. It's the same here live on Tropics. I wasn't really looking into into following weather today, but apparently, yeah, it's there. I see the screen is black for some reason. Oh, there's actually massive delay right now, or not. I have no idea. But I'm already 10 minutes in. So, yeah. There is a massive delay though, because as I see it here on YouTube, I'm still doing the weather models here while I'm already showing the live map. So it's quite weird. Even if the setting is set to ultra low latency. But yeah. You'll see. What we can also see here is if you follow the streamlines here, oh, let me go. My Epic Pen is not correct here. Yep. If you follow the streamlines here, oh, you can see that it's actually bringing moisture from the channel here. And if we overlay what that means in the observations here in the moisture conversions, you can see actually that as this actually moves to the as these streamlines are affecting all this moisture here, you can see that you have a moisture convergence zone here. If we overlay then the temperature here, this is a field showing how much temperature difference, or how much the temperature, no, sorry. It's the, let me see here. It's the convective temperature. Sorry, I couldn't find the words. So actually what you're showing is there's a convective temperature being reached. And you can see this actually by the satellite field. And if you advect all this moisture here, it brings moisture convergence over land. Where convective temperature is being reached, there's obviously a convection going on here. But this convection here, oh, you're from Lithuania? Ah, yes, it's the radars from Lithuania are they're actually already there for a few months, I think. But yeah, so we'll see. Let's go a little bit to Lithuania. Is something happening here? Probably not so much. There's not much going on here in Lithuania. Why? I mean, it's not too far-fetched to see, because if you really look at what's going on here, we have the trough here, but the PVA in this direction, and here actually is going down here, meaning there's sinking motion here. So that's probably why it's not doing anything really. Although later, if you look at the map here, yeah, the Spanish ones, they are unreliable. If you want to look at the Spanish ones, I advise you to pick this one here, the AEMetNet one. And the AEMetNet one, this one is reliable. The sites from Spain itself, they're not really reliable on itself. Why? Because the Spanish Meteorological Institute, their services are uh, behaving, I would say. Right. Also here, the Romanian ones, they're also not so reliable as we would want. But it is what it is. Now, as you can see here, the convection is only getting richer and richer. Right. There's convection going on here as well. Why? If you overlay the cape here, you will see that there's cape there. Right. There's cape there. There's convergence going on here, because as you can see, the streamlines here are moving faster than they are moving here, meaning there's a pileup of low level flow here, pushing the air up, leading to convection here. Also, it's also aided by the moisture convergence tongue here and the convective temperature being reached there. Right? But if you look at the soundings here, oh, if you look at the soundings, for example, oh, yeah, live on tropics. Currently, they're blue. Like if you look at the soundings here, I mean, supercell composite, not so much. I mean, there's only quote unquote 112 storm relative velocity here. Cape is not so bad, but it could have been better. If you look at here as well, the hodograph isn't really all that great. Oh, no, 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 live on tropics. Yeah, the blue is indeed the blue is indeed the radar images that are older than 2 hours. They start, or if the radar imagery, the most recent one is older than 2 hours, then the icon turns blue. But yeah, it might have been better if they were gray or potentially red. Yeah, you have a point there. It's an easy change, so don't worry if you would have wanted this. All right. Now, as you can see here, convection is going on more and more and more here. Yeah, if you have improvements live on Tropics, do not hesitate to share them with us. I would be very happy to actually do some changes. I'm constantly working on the app, so no worries there. One of the next features in the app, or you haven't seen this yet in the app because this is actually the website version. Um, we have added here the range rings of the radar sites. That's not there yet on the app, right? You can toggle them off here in the settings under radar here. You can toggle them off on you can toggle them off here, as you can see. Right? Now, one of the next features that I'm currently working on is push notifications. So what you can actually do, say here in Lithuania, there's a storm coming, right? What you can do, it's not there yet, but I'll show you what you can do. You can draw a zone where you would like to have a watch, a personal thunderstorm watch for you. What you can do is you can actually draw something. You can say, I want a thunderstorm watch for the next hour, the next 2 hours, the next 6, the next 12, the next 24. And if you enable that watch, right, and you close off the app, you will get a push notification to your phone saying, oh, there's thunderstorms in the watch that you have entered, and you will get a notification on that, which is quite handy. You say, much like how I was confused about how that magnifying thing shows the reflectivity values, for instance. Usually that icon can refer to like, oh yeah, yeah, yeah. Yeah, it's how do you call it? It's more of a magnifying glass. Let me pause it here. It's actually a sort of magnifying glass to probe, so to speak. But yeah, it could be a better icon indeed. Like it works actually quite well. And also, if you go outside of it, here, the moment you go outside of it, you can see like you're outside of the radar bound now, right? Which is kind of cool. Um, so let me turn on the extrapolations. Actually, nope, it's here. Like it's nicely moving in that direction. Oh yeah, yeah, yeah. So actually, it's because the app is actually more of a storm chasing app than anything else, right? Because say you go storm chasing, you can say I want this actually to be my chase target. You can say, okay, I want to go here, right? And you can it then mentions here like where it passes. It passes northwest, as you can see. The line passes northwest of that location. You can put the threshold in here, right? So it would be cool to actually draw something. Let me set this one as chase target. You can say if the storm passes here, right? draw a watch here. Oh, let's remove it. I want to watch here if this thunderstorm passes here or is contained or crosses this boundary, then a push notification will be sent to you. You will be able to say, I only want a push notification for strong thunderstorms. I want a push notification for the first lightning. You can all put that in, right? And one of the next features will then obviously be, say you actually live here, right? If a thunderstorm is moving towards you, you can actually also get a push notification saying, "Oh, there's a thunderstorm moving towards your area. It's intensifying or it's weakening." You can get lightning count and all other metrics. Yeah, indeed. Yeah. Uh, you say that if you're at a certain location, you can also set like a range around you, right? And that will actually give you indeed a push notification as well. But that's a feature that's coming, I think, next week or in the coming weeks, right? So let's actually play the loop again. I'm actually curious what these thunderstorms will be doing here, because there's going to be a lot more in a minute, right? So let's see what happens, because as this trough starts to move eastward, it will trigger more and more and more convection. Like for example, you can see that here as well. I don't know if you use this one. This one is so handy because this one shows actually the IPV anomaly with the trough, right? The more green this is, the more potent this trough is, right? Let me turn on here the 500 millibar isotax. Oh, they are on. Okay, it doesn't reach 50 kts here, only here. So upper level winds could have been a little bit better for this convective session. I don't know. You're probably not aware with the geography in Belgium here, but here, for example, this part from here to here, the more you go in that direction, the more elevation goes up. Meaning that this convection is also aided uh, by the elevation. I mean, it's orographic in nature as well. So that's why convection is starting here much better. Oh yeah, if you want to see that how it relates to this one, because as you can see, actually, geopotential height is lower here. Here, it is lower, meaning that as this geopotential height or as this region of geopotential height here moves towards that direction, all right, the how do you say it? The hydrostatic balance gets broken. And what is actually hydrostatic balance? You have gravity pulling the air towards the ground, but you have also the tendency of the air to move into space, right? Because in space there's like zero pressure. Air tries to move upward away from the Earth, but as gravity pulls this air down, there's a balance between these two forces, between the between the upper motion of the atmosphere and the lower motion of gravity, right? There's a balance in between these two forces, and this balance is called the hydrostatic balance, right? And as this trough here with the lower geopotential height, right, moves here, right, this balance gets broken. Why? Because the distance between the ground and the 500 millibar heights is actually lower, right? Meaning there's tendency for air to move up because of the hydrostatic balance that's being broken, right? And that's how you should interpret a, a trough in the 500 millibar heights. I don't know if I don't know if I was clear enough. But I probably already did a video on that. I did actually two videos on that. Here, here, a hail core here. It could be. There could be some hail in these as well, though. Because if you go here, let me see actually. Ooh, this echo is quite intense actually. Yeah, there could be some hail here indeed. You can see that in this one. You can see that in this one here as well. One thing that you actually need to know, if you tilt this upward, right, you can see that the echo is not at ground level. So if you add this radar probe here, right, this echo is actually situated like 1 kilometer above ground. But I would not be surprised indeed if there's hail here. Probably we might see that in the ship as well, but I don't know if the ship will give a signal or not. Let me see. As you can see here, the ship, the severe hail indication parameter gives a signal here as well, right? And since that storm is moving into that region, let me turn off the 3D here. As this storm moves and moves more and more and more towards the east, there could be indeed more potential for hail. So you can see actually that this metric actually kind of works. I don't know if you've tried this already, because there's a lot of observations here currently. We have the severe hail indication parameter, we have the moisture conversions, we have the convective temperature being reached. Oh, my friend, I already did some experiments where in the future I'm going to add the full 3D volumes of the radar here, right? And I actually already did a test where I could render a full volumetric radar field in 3D. Uh, if I can give you, I can probably already show you this. Let me actually, I don't know if I can show you this, but let me see. Maybe I can. Let me find it and I'll show you what I did. And you'll probably like it. It's just a simple test, right? So let me see if I can show you this. Hang on, because I haven't really created scenes on the fly. Hang on. I'll switch the live map currently to here. I don't know if you can see this, right? This is actually a full radar volume um, with all the elevation angles stacked on top of each other. The ChaseBuddy, what it's doing, it's actually making on the fly in real time a 3D mesh of it. You can cut it, you can splice it, you can rotate around it, but it's not online yet. It's just a test that I've done, but it works. And I think you are actually, you're actually thinking about this, right? Or you're mentioning this. This, no? I think you are. If you're not, just tell me. But yes. So this storm can be actually quite interesting. Let me erase all these things for now. Let's check the velocity images. Actually, there doesn't seem to be any rotational signal currently. No, not currently. But it is quite a hefty echo, and I like how it's shaped. You would you would think that it has some supercell characteristics, right? Like it has like a small 9 shape here. It has a you can see the forward flank here in the rain shield. It's quite active. So let's see. It's kind of cool. And it's intensifying and it's growing in size as well, right? Which is kind of cool. I'm curious how this one evolves. Well, let's see what we have here. We have more thunderstorms even now. Oh, no. It's really a complete 3D mesh of the storm. It's not there yet, as I mentioned, but you can splice it, you can cut it down, you can draw your own cross sections. I want a cross section from this point to this point. I want a cross section from this point to this point. Oh, it actually runs enormously well. Um, what I have also done, and I don't think anybody has seen this ever in meteorology, what I've also done is I transposed water vapor imagery, satellite water vapor imagery. I transpose it into 3D, and you can actually see convection growing as it happens, convection collapsing as it happens, all in 3D. And it's quite cool. I think I can show you this. Um, Hang on. It's a it's a demo for you personally. You're probably the only one ever in the world that has seen this in an operational context, right? I mean, freely operational, right? Let me see what I can do here. Um, I have to turn on my coding here, but I can do it normally. Give me a minute. I'll show you something really cool. Let me see if it works or not. So I have it running here. I have to see if it still works. Because I was able to render water vapor completely in 3D. Ah, it's working. Okay, let me switch to that screen for now. You'll probably never seen this, but hang on. So what? Let me go to my other one. I think it's this one. No, it's not that one. It's where's my Chrome? Nope, it's not that one. That's my stream. Come on, where's Chrome? Ah, there it is. So what you see here actually is if you turn off the 3D, right? This is actually how water vapor imagery looks like without 3D, right? Let me refresh the page. You'll probably see some errors here, but that's normal because it's a development environment, right? But check this out. If I turn on the 3D now, this is water vapor imagery. Huh? And actually, I don't know if you know how to read water vapor imagery, but water vapor imagery, you can read it as the whites and the grays are upward motion, the dark grays and the yellows and the blacks are sinking motion. So what I thought was, if I can actually render this in 3D, right? So what I've done, if you turn on the 3D now, you will see the whole 3D imagery of the water vapor, right? And it updates in real time, right? So if I play the loop, it actually already plays, I think, right? But you can pan around and you can actually see that water vapor is a three-dimensional surface, and you need to interpret this as 3D as well, right? It's kind of cool, right? Normally, it will start to update, I think, and run also as the radar is running, but it doesn't seem to do that apparently for some reason. I don't know why. Um, Normally, this is this is showing upper level. You can see convection rising, you can see convection collapsing, but it doesn't do that. It doesn't do that as of now, right? You can see here the valleys in the sinking motion here, and as you can see here, right, this one is actually the dry intrusion of the system, and you can see that the dry intrusion is actually lower, sinking towards the ground, right? But it's not it's not animating for some reason. I have no idea why. There's probably there's probably a lot of errors here. Let me check the console. Oh no, there's no errors really. But I don't know why it's not animating. Should animate. Oh, probably because satellite follow isn't on. Ah, that's it. So check this out, right? It will create 3D meshes on the fly, right? And you can see the convection here grow and collapse, right? Let me do it like this here, right? This is the convection over France here, right? And you can see them actually growing and collapsing as it happens, right? Give it a minute, right? You can see here the spikes growing, as you can see, right? This is actually thunderstorms moving, growing in real time, right? You can see it here as well. The dry intrusion of the system, you can see it sinking deeper and deeper and deeper in towards the ground, right? But I'll give a lecture on this uh, in the future, showing this how this works, how to interpret water vapor correctly, and actually showing you that you can actually see. Check this out. You just see the convection growing in real time. It's just crazy, right? This actually, live on Tropics, this is even running in real time on a phone, right? So it works on the phone as well, right? Without crashes, fluently. You can pan around. You can tilt on the phone. You can pan around. This is all there in 3D, right? But I haven't deployed this yet, right? But it will be part of the ChaseBuddy at some point. Okay, kind of cool, right? I'm practically sure that nobody has ever seen this in this way, right? But it will come later later down the road in the future, right? Let me go here to my live map again, if I can find it at least. I'll close this one. Sorry for the mess here. It's really my first time that I'm doing this, and I'm not really yeah. Sorry. Let's see what you've wrote here, because you've wrote here a number of things. Oh yeah, indeed. Water vapor imagery, you really need to interpret this in a 3D sense. Why? Because let me turn on the water vapor here. Um, Nobody actually, in European meteorology, water vapor is super unknown. And I've never understood this actually, because water vapor is the most shows the most fundamental things, sort of a peek under the hood, so to speak. Right. And as you can see, right, you don't see this in 3D now, right? Because it's not there yet. But this this here, let me give you a small lecture here. Like this here, this is the warm conveyor belt of the system, right? This is the dry intrusion of the system, right? And the dry intrusion is a sinking airflow. And you can see that it's a sinking airflow. Why? Because if you follow the 500 millibar height lines here, right? As a, as a as you follow the 500 millibar height lines, you go from light gray or white to light gray to dark gray to black to yellow, meaning that this air is sinking, right? And if you look here, this dry intrusion is digging so hard into the system that it's actually pushing all this upward, right? Here you have a dry intrusion here. It's the same thing. You have you have a dark zone, as they call it in satellite meteorology. You have a dark zone here, and as this dark zone moves towards the east, right, it's pushing all this air, as you can see here in the satellite imagery. It's pushing all this air upward, right? Because dry air, a dry intrusion, dark zone is actually lower towards the ground or closer towards the ground. White, gray, blue is more upward in the atmosphere, right? You can you can interpret this as follows. Um, how do you say this that you can understand that people can understand it very well? I don't know if you know the term adiabatic compression or adiabatic cooling and adiabatic warming. Air as it starts to sink, right, gets compressed. Why? Because it reaches higher pressure, right? As it starts to compress, it starts to dry, right? Why? Because the air gets warmer in the air parcel, right? The warmer it gets, the more separated temperature and dew point get, right? And this is exactly what water vapor imagery shows you, right? The more water vapor, or the more pronounced the water vapor imagery is, the more rich the water vapor is in the air parcels, right? If it starts to sink, it goes from a high signal in water vapor to lower. Why? Because as the air gets compressed, it warms, it dries, right? And this is why you know that this air is sinking, because it's moving towards the ground, it's drying, signifying a lower signal in the water vapor imagery. So you know that this air is moving down, right? And if air is moving down towards a region, then it's pushing air upward in front of it, right? And this is what you see here in the water vapor imagery, this band here, right? This is all upward motion because of the sinking motion here as the trough moves forward towards the east, right? So I'm planning to do a lot more lectures in the future on these things. But I'm telling you, water vapor is one of the most fundamental and most critical imagery that you can see if you know how to use it. Right. I hope you liked what I've actually explained a little bit so far. If you want to learn a little bit more, just tell me, and we can talk about it. Right. I was just testing out the stream here, but it actually it's actually going rather well. I thought it was more difficult than this. to do. Okay, I actually need to create my scenes and stuff up front. But yeah, so thunderstorms here. They're actually moving little bit more now, or there's a little bit more thunderstorms now, right? So thunderstorm here. Let me turn on the radar here. Oh, kind of cool. Look at this convective signal here. Let me turn off the lightning. Um, there's some hail probably. There's some hail here as well, probably here. So it's kind of cool. Let me see what you wrote here. I suppose you can also perceive temperature in a way, I would guess now, that I'm thinking, because in the lowering, there's cold air. There's cold air aloft, right? So high up in the atmosphere, right? That's actually what the 500 millibar height says. Eh? You have cold air here and you have warm air here, right? And this is actually the hypsometric equation. In my previous video, right? The hypsometric equation tells you. Let me turn on the 3D here. The hypsometric equation tells you that the thickness of a layer, say from the ground to 500 millibar here, right, is directly proportional to the average temperature of that layer. What I mean with this is air with a certain temperature has a certain volume, right? It's the ideal gas law. As simple as that. The relation between volume, temperature, and pressure, right? So if you warm an air parcel, right? If you warm it up, to keep the pressure the same, it needs to expand, right? Meaning that from 0 here, or from 1000 millibars to 500 millibars up here, right? The since warm air, if you warm it up, it expands, right? It takes up more space, right? So if it takes up more space, then the how do you say it? Let me see if I can draw this actually. From the ground up here, like from the ground, this is 1000 millibar, right? Here, this is the 500 millibar height level, 500 millibar, right? So from here to here, here it's warmer than it's here. Why? Because I already mentioned this in my last video, but you can see this here. I mean, the average temperature here, let me show you. The average temperature here between, yeah, black on black is not gonna, you're not gonna see it. So the average temperature between the 500 millibar height and here the ground, right, is lower. It's lower temperature here than from here to here, right? It's actually the distance is greater. Why? Again, warm air takes up more space than colder air, right? So you can indeed see in the water vapor imagery, right? There's actually cold air aloft here as well, right? Everywhere where you have like I advise you to turn on this one here, the pressure at 2 PVU. This is cold, dry stratospheric air sinking towards the ground, enabling this S shape here, right? But that's a whole topic on its own, and I'm going to do a video on that later. Later, not later today, but later in the future. Um, so I hope you liked actually what I've told you so far. Let me turn off the 3D here actually. So you actually was able to follow a live training session here about meteorology. There's a lot more to say, obviously, but I need to prepare for these kind of lectures. Hope you liked it. I don't even know if you're here still, but um, yeah, it's really, I mean, it's difficult, or how do you say it? It's actually, it's really difficult to bring this as material as well. Why? Because it's not the most easy material, right? But I always wanted to in the channel here. The thing that I always wanted to do is bring meteorology in a more digestive manner, where it's more easily understandable for the people, for the viewer, for the people interested in that. That was actually the whole reason why I've created the weather breakdown channel, right? And a lot of these things you actually need to be taught, because if you read all these things, as you say, in a forum or whatever, it's really difficult to digest it. It's super abstract, right? And you actually, if somebody teaches you this in a more digestive manner while showing you what it is, and also bringing some weather models into it to actually show you how it works, how everything is connected. Oh, okay. Well, I was actually live on Tropics. I was actually thinking also in the future to do a live session on soundings. Right. I'm going to put a sounding here. But I was going to do a video on that live on Tropics. I was going to do a video on the complete parcel theory, meaning convection in general, right? And how this relates to a sounding, how you actually see temperature changes in a sounding, how you read a sounding, what is a sounding. So it might be a good video for you actually, live on Tropics, right? I already mentioned the adiabatic. Oh yeah, but soundings are universal. Live on Tropics, you can. Uh, I mean, how to read a sounding is the same in in America, is the same in Europe, is the same in Africa. A sounding is a sounding, right? But I'll show you actually in a dedicated video how to read these soundings. And to already give you some information here, I already mentioned like a few moments ago, air sinking, right? Say, for example, I'm going to show you here in the sounding here. You might like what I draw now, because it might show a little bit things into context here. Say from 500 millibar here, you have the 500 millibar heights, right? And you say, for example, you I need to see the temperature here. Let me zoom out a little bit, right? Say, for example, you have a temperature or a parcel of minus 40 degrees. You follow this line right here. At this point, it's minus 40 degrees, right? So at 500 millibars, if you bring that parcel down, it follows this sloping curve here. And if you bring this air parcel of minus 40 degrees at 500 millibars, you bring this downward along this slope, you just bring it down, right? It starts to compress and it heats up from 500 millibars to minus 40. It heats up, and when it reaches the ground, it's already 10 degrees. Yeah, the elevated mix layer, we do have it. But it's it's not really that big of a difference with the United States. um, you have this in Spanish blooms. Okay, okay, you just mentioned it, I think. Yeah, 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 yeah. Indeed, indeed, indeed. Um, but I will give you actually a full video on that. I need to prepare these things because it's a little hard to now come up with a lecture for it. But I can show you this; it's not a problem. And I can show you how this looks like in the elevated mix layer. But to do that, I need to have a Spanish bloom setup, and I don't have this right now, right? But it's if you want, I can work on that video later. It's not a problem, right? Look at this convection here, how it's actually. Oh, this was an interesting one. Did you see? And it's actually, oh la la, look what we have here. Now this is something that I like to see. I wouldn't even be surprised if there's some rotation in it. I'm gonna remove the rest here because it's a little crowded. Um, okay, that's cool. Oh la la. This is a really, really, really interesting one. There'd be some rotation in here, but let me pick another radar. Ah, interesting stuff. Let me see how this looks like here. And it's moving to the right as well. This is a really interesting one. I don't really see that. Oh, this is cool. Yeah, there's definitely some rotation here, man. Because, let me pause this here. Because if we draw a line from here to here, let me draw a line here from the radar dish to that, right? Draw straight through it, right? There's definitely some rotation in here, right? Because if you look at this one here, this air is moving like this air is moving like this. So there's definitely rotation in that cell. This is nice. This is our first really supercellular structure of the year, I think. Okay, this is cool. We'll have to see how this actually goes in the future. What I'm also going to add in the future here is each thunderstorm, right, will have its own metrics. Live on Tropics, for example, each thunderstorm you will be able to see how much helicity there is in that storm, how much that storm is is prone to producing tornadoes or turning supercellular or whatever. This is a very cool feature. So there's probably, I wouldn't be surprised if there's going to be there's going to be a wind event here because this is a cool feature, man. This is a supercell. I mean, it 100% is. Because as you can see here, there's definitely rotation there. Ah, yes, live on tropics. I am going to also add indeed all these things: correlation coefficient, differential reflectivity. It's all going to be added, right? So no worries there. But that actually depends on the availability. Some it's still Europe. There's no you know this as much as I do. There's no standard here in Europe. Each country provides what it provides. right? So it might be that some countries do not provide it. I don't know if Lithuania provides this in their open data. I'll have to check. But if it is there, I will definitely add it. Yeah, 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 yeah. I mean, I have so many ideas for the app, but there's just not enough time for now. I mean, um, because I have my own job. Um, I have the ah, it has, but I think I'm not sure, but I'm willing to bet that from in Europe, I provide the most data currently. But I'm as a European producer. I'm from Europe as well. I live here in Belgium. I live in this region. Ah, yeah, Kachelman. I like Kachelman too, but the UI and the UX of this site, I mean, oh, come on, I don't like it. Okay, they have good products. You won't hear me say anything bad about it. They have very good products, but um, yeah, it's a German company too, and they don't really give all the data that you actually need. And this is why I started creating the ChaseBuddy. Why? Because I'm a storm chaser myself, and yeah, I'm a storm chaser myself, and I needed radar too, and there was no radar at all, right? So I thought, okay, let's just create an app. It's a free app. Everybody can use it, but it starts to have so many features now. I mean, I think it's also the only app where you can overlay everything that you want on the fly. But I'm not sure about that because I've been following the severe weather case yesterday using WeatherWise, and you could only choose either radar or satellite or or weather models. You could not overlay them. Ah, there is going to be forecasting capabilities as well here in the Chase Buddy. But for now, yes, it is coming indeed. Live on Tropics, no worries. I've already experimented with it. You will get a forecast module in there as well, right? And more models as well. Because currently the model data is only there to give you a bigger picture, to enrich the current situation with some weather models, to show you more situational awareness, to show you how everything interacts with each other, how weather models interact with the satellite, how the satellite interacts with the model data, how the radar fits into that, how the lightning fits into that. And this is actually I consider myself a coaching person, right? I teach a lot to at work also. I teach a lot. I give lectures a lot. I give lectures about meteorology as well here in Belgium. And what I found missing is you could not have one application where you can have everything in one view. And if the moment you start to see everything in one view, it starts to click. You can see the correlation between the satellite and the model data and the satellite imagery with the radar and how it relates to motions in the atmosphere, and you can connect everything together in that way if you start to overlay all these things, right? This is actually the whole main reason why I've started working on the ChaseBuddy. Now, the ChaseBuddy is not an app that I'm working on myself. There's another guy I'm working with, Michael Vragen, cool guy. He helps out with the radar stuff, and there's the infrastructure is done by another friend of mine, but we're both storm chasers, and we are both active in Belgium here. So it's not an app that I can't take all the credit here. So I'm not doing that. Right. But let me go here to this thing here because I'm really curious what. Ooh, check this out. Check this. This is super cool. Like here, you have this V, and then you have this RFD gust front here. This is an RFD gust front, right? And you can see the gust front here along this here. Here, this is actually where the tornado would be. I'm 100% sure this is a supercell. I mean, check how this behaves. This is super cool. Wow. This is actually a real cool cell. Let me turn on the velocity actually, or let's switch to velocity. I have to remove all these things because I have to redraw it. Check it here. Check it here. This is so cool. So if we turn on the probe here, like this is 5 meter per second outbound. This is minus five inbound. So there's a 10 meter per second thing here. Kind of cool. Um, this is the first supercell of the year for me. Now, what we can also see is actually live on tropics. Let me turn off or let me hide the radar imagery here. Oh, sorry. Let me turn it off here. Right. Do you see this here? This is water vapor imagery, right? So if I turn this thing on, satellite follow mode is on. Yeah, satellite follow is on. See, this is convection growing, right? And this is pushing all this as the thunderstorm begins to rise, moisture starts to accumulate below it, right? And this moisture gets pushed upward, right, by the thunderstorm. And this is why you see all that moisture here, that signal here, right? And if you were to look at it in 3D, you will see a spike in there. So let me see if I can turn on the 3D again. I don't have it open anymore. But if you were to tilt this, right, you would see in the 3D actually that this thunderstorm is growing and growing and growing. All right. I really need to put this online. Yeah, it's not that much cape though. Um, because let me turn on the weather model here. Let me switch to my weather models. Hope it's that. No, it's not that. It should be that though. I'm still learning. Sorry if the stream is fucked up right now or messed up right now. Sorry for my English. Um, I can't pull it in anymore. But maybe I can just switch this. No, I can't. Why is this not working? I can pull on this one. I can't switch to my other one anymore. Hang on. I'll create another one. Window capture. Here. It doesn't have that much cape to work on though, because if you look at it, let me remove this one here. If we turn on the cape here, right? This is cape, right? If we turn it on, you see there's not really that much cape, like 18Z, and it's already like 945, right? So it's already more moving towards this. You see that it doesn't have that much cape to actually work with. But what you do have, however, is the following. Let me remove this one again, right? What you do have you have this super pronounced trough, right? And this super pronounced trough is actually pushing all this air downstream, right? Giving rise here to upward vertical motion, right? Since there's a lot of PVA, and if this trough, the more this trough move eastward, the more PVA is pronounced, the more it's actually driving these thunderstorms upward. So they're actually more dynamically driven than they're actually solely relying on thermodynamics, if that makes sense. Right? You can see actually here, you can see the IPV anomaly digging further and further and further eastward. Right here, here you can see that here. Let me turn on. Let me pick another color here. Here, you can see this IPV anomaly here, right? And it digs further and further and further eastward, right? And you can see the boundary moving like that, right? And as this IPV anomaly digs further, upward motion um, is induced here, pushing all these thunderstorms upward, right? And there's also an orographic factor into play, because here, as I already mentioned here, this region there's orographic lift here as well. So all these things combined make that the convection there is more easily induced, right? You can see actually that it's really pushing it upward. Like there's a high water vapor, water vapor signal where this thunderstorm is. Let me turn on the radar again. Let me see how this evolves here. Oh man, this is so cool. Check this RFD gust front here. The RFD gust front on this thing is amazing. Because actually you can see here, oh, let me draw it. So this is actually the RFD here. And you can see the RFD gust front here. You zoom in even more, right? And we draw our features again. Like this is the edge of the forward flank. This is the RFD gust front. This air is moving like this, right? So this is where a potential tornado would be, right? You can see that this gust front is moving like this. The air injected into it, and this is something that I'm going to add in the ChaseBuddy as well. The inflow region of a thunderstorm, right? And what you will see if you plot this, but I don't have this right now, you will see the air being advected towards here, right? Here, along this line, and I can also show this, right? Here, the air is moving up. Here, the air is moving down, right? Because of the precipitation here. All right. So if you were to, but I can't show this right now because I don't have the full radar volume in 3D, but I would be able to show you if I have this. If we tilt this, for example, and I'm going to tilt this like this, okay? Air here Yeah? In this region, air is moving upward, right, into the growing thunderstorm, right? Air here is sinking. Yes, you can understand this, right? Along this, there's an interface, right? And what this is doing is there's air in a sort of spiral way, right? Air is moving upward here, sinking here, and they call this a solenoidal circulation, right? And along the leading edge of the forward flank downdraft, which is this one here, along the leading edge here, what you will actually see is, I can't show you this right now, but there's a solenoidal circulation here, right? Up, down, up, down, up, down, up, down, right? Up into the atmosphere, right? And as this air is getting, oh, I'll have to pick another color here. As this air is going here, right, being funneled along this forward flank downdraft, there's a vector here stretching this vorticity upward as it rises here into the thunderstorm, right? So this is the main driver of the low level mesocyclone, actually. This solenoidal circulation stretching stretching the horizontal vorticity into the vertical, right? I made a video on that as well, I think, but I don't know if you saw that video. Um, so this is actually how that works. I don't know if you actually still here or not. I'm just speaking out loud here, right? But this is how the solenoidal circulation works, right? Man, the cell is super cool. Oh my god! Check this here. I would not be surprised. I would not be surprised actually if there could be a tornado here. Let me turn on the velocity imager. Oh, check this one. You have the same thing here. There very well could be a tornado here, and it's the same here, man. I mean, draw a line from here to here, and you also have this couplet. Eh? You have outbound, you have inbound, so there's definitely vorticity here, and you have the same thing here. So draw a line from here to here, draw a line from here to here. You have outbound, inbound, uh, outbound, inbound as well. It's kind of cool. Um, Man, this is crazy. And look how the signal is being shown in the water vapor imagery. This is a crazy cell, man. I mean, this is definitely hail in there. And you also need to be aware that this signature, if you turn on the 3D, this signature, this is not far from the radar. So if we turn on the probe here, I mean, this is only like 200 meters above ground at the Sacho. I mean, this is crazy. This is this is really crazy. So you would see that this here, the low level rotation signature here is only 300 meters above ground, right? So this one could have, yeah, this one, as you mentioned, it could have damaging winds. It could even have a tornado in there, right? But I don't see this right now. I don't see a real tornado currently. What I do see is probably a heavy downdraft here, right? Why I wouldn't think there's a tornado? It could be, but why I wouldn't think there's a tornado in here? I mean, if you turn on here if you pick a sounding in there, right? Let's see. It could be. Let us look at the low level wind field here. I wouldn't think there's a real tornado in here. Uh, Although, yeah, there probably is, and or it could be, but as you can see, none of the severe weather parameters actually give a signal. And what you would actually need here for this to be a tornado sounding, what you would need, or what you would prefer rather, is that you have like a curving, that you have at least like a curve here where the low level wind is moving like this here, and the 1 to 3 kilometer wind shear vector is turning that way. Because as you can see here, there's a lot of streamwise vorticity in this point, but as you can see here, there's not, right? So it doesn't use the lower levels very nicely, but from like 1 kilometers, there's like very nice streamwise vorticity here. So supercell, yes. Tornado, I would not count on it, but it could be. Let me see what you wrote here, because you mentioned something here. Sorry, I haven't followed you. Let me see. You say, in fact, this is probably bigger than the event from some time back when we had storm from France towards the Benelux. Yeah, it is certainly bigger. Convection seems to be initiating rapidly, but I wonder how much energy it has to work with. Yeah, I show you the Cape. So for such limited Cape, it's doing extremely well. Yes, the reason why it's doing extremely well live on Tropics is because of the IPV anomaly that's pushing all the convection upward, right? I think it's surface based. Why? Because if you turn on the 3D, right? Let me go to precipitation here. If we turn on the 3D, right, and we turn on our indicator here, right? I mean, this echo is 300 meters above ground. So I would think that it is not elevated. It is surface based, although um, although I don't really know right now. But it seems surface based. Why? Also because like uh, there are some high hills here as well, right? Meaning that it's already like 400, 500 meter up. So I would guess that it is surface based. Um, I would think the same for these as well. I mean, just look at these signatures, man. These are really sexy signatures. Like both of them have a RFD gust front, right? Like this. Same thing here, but bigger. They both have RFD gust front. Tornado might be here, although again, I don't really see that. Yeah, live on Tropics. This is the reason why I've opted to, or why we've opted rather to put the complete radar network of Europe in there, right? And you can see everything in correlation now. You can see the reflectivity in correlation with the model data, in correlation with the satellite view, in correlation with the streamlines. Let me remove this. Oh, sorry. Let me remove it for now. I mean, just check how this IPV anomaly here. I mean, it's so crazy to see how this IPV anomaly here digs further south, right? Pushing the air upward here in a sort of baroclinic leaf, right? And here, where the thermodynamics are favorable for convection, this trough with its IPV anomaly digs down As it digs down, it leads to upward vertical motion downstream of the trough here, right? But indeed, since they are that close to the radar, the resolution is so high here. I mean, and you have to, if we take this one here, I mean, you still see the structure, right? But this is like, wow, this is crazy. I mean, and this is only like how far from the radar? I mean, as you can see, this is actually like 30 kilometers from the radar. Man, this is crazy. Huh? Let me see if we can see some high winds here, right? I don't really uh, see signs of a tornado, though. Could be, could be here, but if it were here, then this is not a tornado. Why? Or it might not, probably not, because this here moving towards the radar, this is moving away from. So actually, this is a cyclonical or an anticyclonical circulation, right? Normally, what you would need to see is you would need to see the opposite, right? You would need to see that this is moving in that direction, this is moving in this direction, but this is red, so I don't know. This is moving away from. So guess there's a lot of I guess there's a lot of wind here, probably. But we'll have to see. Let me turn off this, turn off this, turn off this, and remove that one. Let me check at Paris here. There's some thunderstorms happening there. In the south of Paris. I don't see this right now, but you mean on reflectivity probably. Which one? Which ones do you mean? Do you mean this one here? These? Do you mean these here? Because yes, and they are related. Like they are related to here, this one probably. Like there's no really. You probably mean these ones, right? Or are you talking about these small convections here? You're probably talking about these. Ah, yeah, probably. Now, the reason why these are firing is twofold. Why? Again, you have this IPV anomaly digging southeast here. So you have this IPV anomaly digging southeast, right? You can see this in the satellite imagery. It's moving in that direction, right? While it's moving in that direction, you have at the low levels check check the streamlines. What these streamlines are doing is they are pushing all this moisture from the channel towards here, right? You can see here in the water vapor imagery, right? That's that's why it's so cool to overlay everything. Oh, fuck! I erased everything. Yeah. So if you really look at the water vapor imagery now here, right, you can see that there's an upper level boundary here as well, right? Because as you can see here, this is an upper level boundary, right? Drier air in upper levels here, which is probably the reason why there's hail here as well, right? Right? There's an upper level boundary here. There's an upper level boundary here. There's an upper level boundary here. Why? Because this is more white than this. This is sinking air. This is rising air here as well. So you have two boundaries here in upper levels, while at the low levels you have this moisture streaming towards the mainland of France. And if you then overlay here, the motion conversions, for example, I'm willing to bet my ass off that you will see a signal here. There's a signal here, right? Just the south of France here, right? You can also see it here by the 10-meter streamlines. They are streaming over the mainland, but they are slowing down here, meaning there's definitely low level conversions. There's upper level boundary here. There's upper level forcing moving in from the northwest. So all these things combined actually make it so that probably this convective train will dig a little bit deeper south and deeper south and deeper south as time progresses. But the models are signifying more a convection in this region here and to the east of Belgium. But we'll see how it transpires. All right. So your intuition might be right, the live anthropics, because as you can see here, it's digging more deeper south. Let's turn on the live lightning here and the history, right? You can see already thunderstorm there as well, right? Probably because of this one here. So this one is already becoming electrified. You can see here, let me turn on the extrapolations. You can see here that the bearing is actually 109 degrees, right? While if we turn on the sounding, right, this is a good thing to see. If you turn on the sounding now, you will see that the model predicts that the storm is actually moving towards the. Okay, it takes a little while before the sounding is there. I need to fix this in the back end. It's something that I would really need to do. If you look at here, right, the model says that a storm motion more towards the east northeast is this. A right mover is moving more in in that direction. And this means that this one here, right? Oh, you see the direction already 109 degrees. So if we draw our Cartesian frame here, right? Our Cartesian frame here, the normal storm motion was predicted like this. Right mover was created was actually in this direction. So we have a right moving supercell here. We have the same actually here, right moving supercell there as well, right? So we have two right movers currently um, over Belgium and the region of France, or the border region with France. I'm actually curious if because I just did an update like last week on my thunderstorm detection system, right? And it should now show these bearings in the right direction. I made it so that it detects right movers much more faster, and it detects deviant motion much faster, and it really does, because as you can see, if I turn on the storm tracking here, right here, this one, it really detects deviant motion here, right? And if I turn on the storm extrapolations here, you can actually see that this is actually indeed moving in the 105. This one is moving actually in the 101. I'm pretty sure that this one in a few later timestamps will also start to exhibit this exclamation mark here. So this exclamation mark, live anthropics, what this is actually signifying, this is showing you an indication where there is a detection of a right mover, right? The more it starts to move to the right, or the more persistent it starts to move to the right, you will get this indication. Okay, you will see this in every storm that you look for on the ChaseBuddy. Right. Well, this is actually kind of cool, man. I'm going to do this radar imagery because this one has both of these in. This one has both of these in the radar frame. This one is a little bit too far. Right here, this one. I mean, it's there, but it's not as pronounced. Okay. Let me turn off the lightning here. Man, this is really cool. These streams. Yeah, I saw these thunderstorms popping up live on Tropics, and I thought, why not actually do a stream now? I don't know how you think about stream. Did I Are there things that I can improve? Just tell me if there's stuff that if there's stuff that I'm doing wrong. Just shout here. I mean, there's no right or wrong answer here. I just thought I would do a stream and see how it goes. But as the situation develops, it gets more and more and more interesting, actually. So it's kind of cool. So again, it's the first time that I'm doing this, guys. Guys watching here, so don't kill me if I'm doing so bad here. But all things considered, I'm doing rather well. Yeah, I mean, sorry for this. I mean, I'm. It's my first stream ever. Um, so if you look forward here, oh yeah, yeah, the weather breakdown live stream. Yeah, I would. Yeah, yeah, you're right. You're absolutely right on this. Um, but yeah, it's kind of cool. So I'm going to turn off this one. Probably there's going to be a notion here as well. Probably if I am going to turn off the extrapolations, right? Let's look at how this behaves, man. This is crazy. What I miss in the ChaseBuddy is I'm not able to pick any. I'm not able to pick any elevation angles currently. But yeah, it will be there in the future. I mean, just this one is getting more and more and more interesting by the minute. Eh? Just look at how this digs down here, right? And then creates this RFD gust front. I mean, I'm really curious if there's going to be an echo wrapping around here. This is going to be so crazy to see in the ChaseBuddy. I mean, it's only the first year actually that we have all these products. So for me, Live on Tropics, this is the first time as well. So your my enthusiasm. I mean, I can't hide my enthusiasm as of now. It's crazy. Um, let's check how the reflectivity looks here. I mean, there's definitely hail there too. These are probing a little higher above the ground. And higher above the ground, right? Since this radar is higher, you do see a wraparound here, right? Because now, if you look at it really, right, we have this shape, you have this wraparound feature, and you have this RFD gust front. So there's probably a hook echo ish thing going on here. Not really wrapping around, not really occluding, but it is probably there. We'll just have to see. Look how crazy this shape is, man. This is like a really first significant warm season thunderstorm echo. This is crazy. Look how this is now breaking up here. If you rock this back and forth, right, you see here that here you still have a pronounced one cell here, right? The echo here, RFD gust front, right? RFD of the circulation wrapping around it, right? RFD gust front here. As you move forward in time, sorry, as we move forward in time here, you'll see that the RFD gut front is actually getting more pronounced here. Let me erase these things. Let me do it again, right? More pronounced, right? If you go a little bit further in time, right? you see that this RFD gust front here has really broken off this entire, or sheared off the entire piece of the cell here. Yeah, to be very honest, I was also a little bit surprised about these echoes actually today. Why? Because I thought, okay, the cape is rather low, right? But it's really significant, even if the cape is low. But as you could see here, this is no longer like a pronounced cell. This is going to probably shear off, right? Because of the RFD gust front, it's creating its own cell actually, or the RFD gust front is popping up an own cell now. But I see you are educated as well in the severe weather live on tropics. Uh, you should do some videos as well, man. I mean, because I'm 100% aware that in Lithuania there's also some nice potential for thunderstorms, especially in the warm season. Look here, man. Look here, guys. What you see here is we have here an appendage here sticking out where the where the RFD gust front is, right? We have a clear slot here. You can see it actually in the precipitation, right? If we move it away, right, you definitely have a clear slot in the precipitation field here, right along the location where the mesocyclone should be, right? RFD gust front here. I'm really curious how this looks like, man. Uh, I haven't. Oh man, look how sexy this is. Look how this evolved, man. You can really see the RFD gust front kicking in from here. So from here, you have this RFD gust front. So the RFD gust front is moving from here in that direction. If we follow it further, let's see how this behaves. Check this RFD gust front, man. From here on out, the RFD gust front is really kicking in, making a bowing feature in front of the cell. You see this thing here appending. Let me switch to velocity. Right? The velocity is really diffuse, as you can see, right? I said this, yes. Why? Because the models, the not the cams, not the convective allowing models, but GFS for example, as this trough digs eastward, right? As this trough here moves further east, right here. Oh, as this trough moves further east, right? The forcing will move from here more to the east as well, right? Leading to higher precipitation in there as well, right? Also, if you look at it, I mean, by this time, there's not gonna be a lot of cape here. Let me pick a sounding. Not gonna be a lot of cape right now. What would also be a good factor here, live on tropics, is that you can go forward in time here as well in the soundings, right? That's something I need to think if I will add this or not, right? If you look at it, like thermodynamics wise, there's not really like from 1000 to 850 millibars, there's only like 4.8 degrees lapse rate, right? Which is not something to write home about, right? There's also like a warm advection regime here, right, where you can see the cap, right? So there's not going to be enough cape there, but I do see some potential for convection. Why? Because there's going to be upward motion anyway, right? I don't know if it will be electrified convection, right? Because for electrified convection, what you would need to have a cape profile, right? More like this, extending high into this region here where charge separation is possible, because this is actually the reason the supercooled region, right, from -20 to zero, and that's actually where the supercooled region is, where grapple is actually formed. Because if you have a thunderstorm, you have the cloud liquid water content, the LCW content, is being funneled into the thunderstorm. The thunderstorm grows with the liquid water entering the supercooled region. There's a lot of turbulence in there. Grapple gets formed in the supercooled region, and this is the region where charge separation is. So if you have a cape profile which only reaches this level, it should reach actually much higher, so that there's a lot more cape profile inside that supercooled region where charge separation is possible, leading to electrification of the thunderstorm. The GFS, this is actually also always my go-to. Why? Because started my um, I started my meteorology journey, I would say, using the GFS. The GFS is very good at early showing signals of something. It's highly erratic, I know, but if you know how to read it, you actually can see that the GFS sometimes, actually mostly, comes with signals early on. It shows a signal, then it goes down again. It shows a signal again, then it goes down again. It fluctuates a lot, and then it starts to solidify on a certain outcome. The European model, I feel, is more gradual, moving towards an outcome. I don't know if you have seen the same or if you know what I mean. Um, Man, I'm going from one thing to another here. it's it's chaotic. Oh, you use the AI models? I haven't really used them, to be honest. The AIFS, yeah, I have access to it, to the data. I've already looked at the data. I can render the data, no problem. But I really haven't used it myself. What I do have, however, is I have my thunderstorm detection system currently, right? I have been creating an AI model for it. So parallel, there's an AI thunderstorm detection system running as well, right? But I haven't used it. But the AIFS, I haven't used it. I am gradually introducing AI in my workflow, though. This is super cool. Let me see if we can see something here. Just check here. I mean, this is definitely a supercell feature, man. Here, this one, it's crazy. Yeah, maybe I should take a look at this AIFS models. I haven't looked at it, really have not. But maybe times are changing, so why not do it? So let's look at the reflectivity here again. Oh my God, check this out. This is so cool, man. I mean, look at this. So you have this feature here, right? You have this feature here. Now you have the RFD gut front, and check how the RFD gut front here is wrapping around. So there's the RFD gut front here. If I zoom a little bit further in, right, and we draw here our things we have here, the boundary of the FFD. This is the forward flank downdraft here, this part, right? Forward flank downdraft. We have the inflow region here, right? Solenoidal circulation here. Here we have the mesocyclone probably, with your RFD gut front moving here, and see how it wraps around here, right? So this is probably the RFD gut front moving here, right? As it moves here, it creates a deformation zone, right? And this deformation zone, since you have airflow moving like this in the inflow of the storm, the air is being diverted in that direction and is being diverted in this direction. So what you have here is you have RFD cooled air moving into the updraft here, along with the moist air, moist thermodynamic air, along with the rain cool downdraft here, right? Leading here to probably, there's definitely going to be a wall cloud in there. Man, I would really like to, how, what I can do, there's a webcam here for this station because I live in Belgium. I know that the Wiedemont radar site here, let me erase everything. The Wiedemont radar site, has a webcam. So let's see if I can, if I can, let's see if I can show that webcam actually. Okay, so what you could probably see, yeah, it's dark right now, right? Ah, it's darker right now. But what you could see on the, let me see if I can show you this. Can I change this live map potentially? Yeah, you can see here the Wiedemont radar site. You could see the towering. You could see the towering convection here. At you could see the towering convection, but as it moves, I mean, it's a little shame. Huh? Yeah, it's too late for now to see it in the radar, or to see it in. Man, how sexy these storms are, man! This is really crazy. Check this echo, man. I mean, crazy stuff, crazy stuff. And this is only the beginning of the year. Eh? I mean, this is the first convective situation of the year. These are crazy cells, man. These are really crazy. Let me see the backside of it. Oh, reflectivity. Let's check at the backside. Even here, so far from the radar, right? Even so far from the radar, you can see notions of this RFD gust front here. I mean, just check it here. You can see notions of that, right? Crazy. And how far is this from the radar? I mean, we have to check it. How far is this? Or we can check it. From this radar, it's 100 kilometers away, right? 100 kilometers away. And if we turn the 3D on and if we put our radar probe, right? 1.18 kilometers here and here 1.31 kilometers. 1 point, yeah, 1300 meters high above the surface. This is the first time that I'm actually using the ChaseBuddy in such a manner, live on Tropics. I'm. I think so too. Live on Tropics. I think so too. I think that they're gonna be like, please survive, please survive, please survive. And I think the pictures of that are gonna be rather amazing. Eh? You will probably see a really defined updraft, right? With a corkscrew potentially. I don't know. Eh? Just thinking out loud here. So what do we have? Have our I'm gonna turn off the 3D here, and I'm gonna turn on my thunderstorm extrapolations here just to see how we are going. Check this one here. This one is moving in that direction. It is correct. Yeah, it is correct. Man, these cells are just amazing. There is some interesting stuff here as well. Yep, let's check it. These are also starting to move to the right here, man. These ones. These are also very interesting cells. Also right movers, by the way. Check where this one is coming from. Man, crazy how active these are. I actually wanted to go storm chasing now, but I didn't. I was just texting my friend here to say to tell him, look at these cells, man. They are just crazy. And not only this one, check here as well. They will probably merge. Yes, they will. They will. They will probably merge. You can already see, man. This is super crazy, man. This is cool. This is cool. You can already see that they are starting to merge and interfere. Because as you could see here, you have a very good eye live on tropics because they are moving towards each other. And the precipitation field of this one is already interfering with this. So I'm guessing this one will start to collapse in a bit. Here, this one. This one will probably collapse in a bit. Why? Because you can see the rain shield of this one starting to interfere with this one. This is cool. Let me see what else. Let me see what else. Let me see what else we can see here. Let's put the. Let's put the dew points actually here. Low level is coming from here. So you can see the streamlines moving actually towards the north, from the north here towards the south. right? So this will probably die out. I'm not a meteorologist as well, live on tropics. Just to be 100% clear here, I don't have the title of meteorologist. I know some things about meteorology, sure, but I'm not a meteorologist, or I can't grant myself the title of meteorologist. Why? Because I don't have a degree for it. I have I'm keen in physics. I know my thermodynamics. I know meteorology, but I'm not a meteorologist per se. Right? I'm a hobby meteorologist, as they call it. But what I am is I am a software architect. My daytime job is I am a software architect, right? And because of my software architecture knowledge, combined um, with my interest in weather, right? The ChaseBuddy came to fruition. But live on tropics, I have to be 100% clear here. I mean, everything you say, they do make sense. So don't sell yourself short. You know stuff about weather. I mean, meteorologist or not, I mean, you know your stuff, which is cool. Don't sell yourself short. Um, you can already see that my thunderstorm detection system starting to look at them as one coherent structure as well here. Probably if we turn on the lightning here, right? History, you can really see, right, that it's starting to fill the void here. Why? This is the reason why it's starting to see them as enlightening, right? As one coherent system. And you can see it in the precipitation field as well. The precipitation field is starting to merge, interfere. So you can actually already or you cannot say that they are distinct without any influence from one another. Ah, okay. You're into tropical site, yeah, probably live on tropics. But do you have actually a web page or something, or something something where I can see your stuff, or do you create videos, or because you made me quite curious actually. The right moving nature is starting to disappear as well a bit in these cells. I mean, if I remove the storm tracking here, right, you can see actually in the track here as well that it starts to wobble. Like here, then it moves like this, then it's starting to move like this again. So it's wobbling a little bit. It's starting to lose its right moving signature here. And the same thing is happening here. So from here, at this point, it started to right move. Then from here, it's starting to move like this again, right? So we have some regime changes here. We have regime change here. We have regime change here. Same like this. We have regime change here. Then it started to right move. And then you can see it curves a little bit up again. So it's gradually starting to move its right moving signature here. I'm really curious what will happen in the next coming hour here. Oh, Weather Action Europe. I think I'm going to follow you. You can follow our Chase group as well, on Facebook if you want. Our Facebook page is the Chase Buddy. Oh, no, the Chase Buddy is Chase to be. Chase to be. Uh, Let me write it down here for you. Um, it's pays to be. And all our updates for the app and such, what we are doing with the app is all going on there. So follow us if you want. Not something that you really need to do, of course, but if you want, you can, and you get some updates on the app as well. Um, these cells are so amazing, man. Let me remove the history here. You can clearly see that it's really coming together here. I wonder what the velocity image says. If he can see something on the ground or not, probably not. No. Let's switch actually to reflectivity. You don't really see anything worth. It's all outflow right now. So as you can see here, if we turn on this one, right, we we already talked about the RFD gut front here. If you remember, like we have the RFD gut front wrapping around here, and if you check now if we turn on the velocity actually, right, you'll see here, right, this is all air moving towards it. This is all outflow right now. It's all outflow dominant currently, which is probably the reason why it started to lose its right moving characteristics. But as you can see, this is all outflow right now. Right? Um, and you're saying, yeah, you wonder if it will try to become more of a squall line of multicell. Yeah, if these merge here, then it might. It might very well be. And as you can see here, what are these temperatures or dew points? Dew points. Temperature here is still like 20 degrees, 15 degrees, right? So it's still warm at surface, right? Dew points, nah, foresty area, I kind of understand. Yeah. Um, Dew points are not so great, meaning that Cape will probably be lower. But um, yeah, you can see the stark contrast here. As you can see here, right, higher dew points left of the line, lower dew point towards the right of the line. So probably as time progresses, um, it could be very well they that it dies down. But it seems to correlate rather well with what the GFS was saying about the situation. Because if we go a little bit further or go to our thing here, I don't know if you see what I've done here. Here, this one, right? If we turn on the weather models here and go to our, oh, there's something in the way here, to our precipitation here, right? Here. This is what the precipitation field shows according to the GFS. And as time progresses, see what's going on here? Bam, right? During the night, it starts to increase. Why? Again, because there's a magnificent potent trough here, right? The magnificent potent trough here, along with this IPV anomaly, digging southeastward, as the gradient between the ridge here and the trough here gets greater, upper level motion will start to increase. So there's probably going to be some hefty convection over the night. but I'm not really sure if they will be electrified or not due to the absence of cape. But yes. But I would not be surprised if they evolve around that, around, or if this evolves into a squall line as well. But I don't really know what will happen further downstream here. Look at this, almost completely starting to be ripped apart here, right? Almost completely being ripped apart because of the strong dominant outflow right here. Let me take black. Because of the strong dominant outflow here. Check how this is no longer like this, but the outflow is so strong that it actually reorients the gust front like this, minimizing the way in which this air is being injected into the storm. Eventually, the storm will probably die out. Go further in time. See the same thing here, by the way. Here you still have this RFD gust front, or like this nice signature here, right? With the RFD gust front attached to it. As time progresses and the thing moves towards the east, you will see that it's no longer that shape, but due to the outflow here at the back of the system, it reorients the whole thing like this, which is the same thing what's happening here. So we have this wraparound here. It reorients the line like this, signifying probably a transition from uh, one type of thunderstorm to another, more into perhaps yes a linear system, but we'll have to see. Um, Cape is higher in northern France, yes. Um, and actually, what I've done is let me go to my weather models again, and you probably haven't seen these yet because I've created some other weather models right now, right? Check this one here. So if we go here, what I've done is I've the SPC, the Storm Prediction Center in the States, right? They create their threat levels like thunderstorms, marginal risk, low risk, enhanced risk, medium, and high. What I've done is together with a friend of mine, we've made this operationally. And so what it does is it looks at the GFS, right? I only have this at the GFS. I need to redo this for the European model as well. But if you go here to the threats, right, you actually see here the same the same parameters, the same thresholds as the storm prediction center uses, right? We have tied this to the model, right, to show you what the risk is here. So if you go here, right, as time progresses, the risk for thunderstorms and the marginal risks start to decrease south outside of the domain. Why? Because Cape is also moving outside of the domain. So the the chances for thunderstorms are going to decrease the more as the trough digs southeastward. Sorry. Now let me go back to my thing here. This is so cool. They're really, as you could see, the precipitation field is really starting to fill in right now. It's really starting to fill in here. Here, as you can see. So this gut front is starting to interact with this cell here, right? I'm really curious what will happen in the next coming half hour if they will merge into one cell. Merges more often than not are destructive. Huh? It could be constructive, but most mergers are seen as destructive for the thunderstorms themselves. But we'll see what happens, right? Again, if you look at the system as a whole here, I mean, we turn off this, right? Let's turn on the infrared here. Let's turn on the infrared. See what we can see. Too bad that what we have here in this wind field here, you don't you don't have it here. I mean, I was very curious what would have happened now if the upper level winds were stronger. If wind shear was stronger, what would have happened? I mean, I might have not been surprised that there would have been a tornado or two today. To be honest, check this one here. Also an interesting structure. Man, these are really cool structures. If you pick this radar site here, you can really see them racing towards each other now. All right, because if you check here, this one is moving like this, or the trajectory more like this. The trajectory is more like this. So around Luxembourg, they're going to start merging. So you're probably right. This might morph into a squall line. But let's see how it transpires. Right? Yeah. This one here, I know. Let's pick this radar site here. Remove these things. Here, talking about this one probably. And look at the others as well. Wow. 4 supercells, man. 4. Wait, 5. 5 supercells. All of the detections that you see here in the thunderstorm detection are supercells. All of them. This is so cool. Um, like this one is weakening, right? But I can see a reinvigoration here. Like it weakened from here to here, and then it starts to pick up again. These are going to merge definitely, man, as you mentioned. This one is probably this one weakening as well. It's gonna intensify a little bit a little bit afterwards, I think. Oh yeah, the last scan, yes. In the last scan, you can see it weaken. Yep, from here to here, it's weakening, and it's growing smaller as well. The area is decreasing. The flash rate is decreasing. Yeah, pretty curious about this one. Also a weakening trend. This one, as a system, is still intensifying, and I think I see new scan intensifying. I thought so. Yeah, this one too intensifying. This one is still weakening a bit. So this one is kicking up. You can see it already in the storm here. I mean, from here to here, right? This region here was a little bit weaker, starting intensifying right now. You can see the you you can see the bump in the graph as well, right? Here as well. Lightning count is picking up again. Cool. These, I'm really curious what's going to happen with these here, because you can see here this track is almost completely done. I think this will start to be weak, to get weakening. This will start to weaken as well. And afterwards, you can see the trend already. You're right. Lightning doesn't tell the full story. That's true. And also, the data is coming from Blitzortung, and you probably know, if you followed the weather yourself, live on tropics, that Blitzertung is not the most reliable in terms of data source, right? Because if you if you're looking at a storm, for example, and it's a stroboscopic lightning, sometimes half of the lightnings are not even picked up by Blitzertung, um, by their system. I mean, so indeed, lightning doesn't tell the complete story at all. Cool signatures, man. Here, they're really cool. Cool signature, man. And also right moving here. You have four right movers, man. 1, 2, 3, 4, 5. Really. And the extrapolation is doing nicely, I think. Yeah, I think it is. Look at this. I'm really, really happy with it. Um, really happy with the app as well. Like, for the first time, I always wanted an app where 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 I wanted to look at weather the way I look at weather. Now, the way I look at weather is not necessarily the same as the way you look at weather, or the way somebody else looks at weather. But I always missed overlaying all these things to see everything in correlation. Check this merging into each other here. Lavantropics, I also think the same. Like, for example, if lightning strikes, I'm going to draw it right now, but it's stupid to draw, but you'll know what I mean. If lightning strikes, then branches off. That I think is in Blitzrichtung also a new signal. Branches off, branches off, branches off, branches off, branches off. Every branch, I think, shows a shows a detection in Blitzrichtung, but I'm not sure. I could be wrong, but that's how I think about it. I could be wrong, huh? But I might not be surprised that it is. Ah, yes, images and stuff. Yeah, but to do that, you need to have a community. Huh? Like the only community-driven aspect that I have right now is the shooting locations here. Right, so I can pick a shooting location, and you can see actually the view. Right, you can put your car in there. So yeah, it might be a good idea indeed to have like storm reports where all the chasers active in the field are are indeed sharing what they see. That would be a good feature indeed. Yeah, this is just crazy. I should have gone chasing, man. But I'm really happy that right now I can actually put the chase buddy as it currently is to work. See how it behaves and actually follow storms with it. It's kind of cool. Yeah, this is gonna be this is gonna be disastrous for this weakening. As I mentioned, it's already weakening. The trend in size is gonna be stable, but it's gonna be more compact if they start to merge. So then the only thing left is these here. Eh? This one, it's not really intensifying any further. They're still fluctuating here, right? Stagnating as well. I'm gonna turn off the shooting location because we don't really need it. And the thunderstorm detection system is doing its thing. I'm happy. I wonder how my AI is currently picking up on that one. So cool. Let's see how it goes here. You see that it starts to break up here as well. Huh? Here, like this cell is starting to break up here as well. Let's pick this one. Yeah, starting to weaken here. Oh, this one will die down. This one is kicking over. Maybe, as you already mentioned, it will go as south as France. Eh? I'm just checking what you mentioned here as well. Eh? Oh yes, yes, yes. Maybe actually they could be submitted to the ESWD. I actually contacted them, the ESWD, um, if we could build for them a whole ecosystem based on the ChaseBuddy, but they haven't replied to me yet. there was an auto reply saying that they're they're unavailable for communication as of now. I'm not really following the Astrophex and such. I used to back in the day, but I'm not really using Astrophex. Essentially, what you can do is you can overlay the Astrophex forecast on this on the ChaseBuddy as well, but haven't really thought about it. Oh yeah, yeah, it is. It is super interesting to see. I also don't know. Just a question, Live on Tropics. Can you write me a question? I'll answer it as soon as I see it, just to see how much the delay is between you conversing with me and me replying to it, if that's okay. I'm pretty curious. Oh yeah, they lack funding indeed. Yeah, like they have a whole test bed with the test. How long did it take for the test for you to come back? Give or take. That's just crazy. I never thought this day was um, gonna be so cool. I haven't really looked at the weather. Ah, did you hear me? Yeah. Okay. So, um, what? Can you write test again and see a little bit how long it takes for me to say something back? So you write test, I say test back or something, so that you can see how long it takes for me to reply to you, or or after how long you hear my reply. Because I'm guessing there's a lot of delay actually. Yes, you. Test back. So how long does it take for you to write something to me in the chat, and then I say something back, for example? Is it long? Is it not long? Is it doable? Oh la la. That's not. Is that good? Is that bad? I don't know. I don't know if that's good or bad. I don't really have a measure. completely broken up right now. The cells here. They're gonna die, I think. Really curious be how these will be how to say it, if they will survive or not. This one is still fluctuating here. This one is probably, I don't know. You have to also be aware here, as you can see, this cell here, right here, this cell here, this one here, right, is moving in that direction. But as you can see, this precipitation region, this precipitation region has already been moving from here, right? Here. But this precipitation region came from here to here. So as this storm moves here, this region here has already been stabilized. Right? This region has already been stabilized. So as this storm moves towards there, this one will probably die out. That's what I think. Um, Live on Tropics, how often do I update it? Well, hourly. Why? Because let me tell you a little bit what these observations here are. CAPE is actually predominantly a model output, right? But what's done in the calculations is the lower level is being substituted by the observations, right? So the lower levels they have, for example, 12 degrees or 18 degrees or whatever, while the model says it's 16. We substitute the lower levels for the real observations and then we recalculate the CAPE, right? That's why it's under observations. The observations change each hour. Each hour there's new data, right? So the CAPE, hourly, SYN hourly, motion conversions, all these here, all these under observations are actually hourly. If that answers your question. Satellite is each 15 minutes, right? Um, Storm tracking is each 5 minutes. Storm tracking is each 5 minutes. Radar also each 5 minutes. Satellite each 15 minutes. And yeah, that's about it. As I mentioned here, these storms are going to die here because they will probably not survive here. As you can see here, this precipitation here, right, has moved from here to here, right? Meaning that this whole region here has already been stabilized. Here, this whole region has already been stabilized. So as you see these tracks here moving from here to here, moving from here to here, right? Moving from here to here, these will probably not survive because of the stabilization that this precipitation has already done. Yes, live on tropics, I am 100% aware, indeed, that a Metsat, they provide these images, but to use these images, it costs you €8,000 yearly. For €8,000 yearly license, you can use that imager. Obviously, I can't pay for this, right? So yeah, no, it's not free. The image that I'm using is open source, yes, but the imagery that I want, the high res imagery, right? That's €8,000 yearly. I'm not kidding him. I just did a this week. I just did an inquiry to it for it, and €8,000 per year. Yes. Now, to be frank, this data is also coming from a Metzote, but it's not raw data. I can't change the data. What I did change, however, is even even if it's not raw data, the water vapor imagery here, right? This is actually I get this imagery as black and white, grayscale, right? What I do, however, is I read in that data. And what the ChaseBuddy is doing on the fly, it's recoloring it according to a color scale that I provided. So it's reading in the grayscale imagery from a method, the free one. I recolor it so I can enhance it to show the dark zones, to show the dry intrusions, to show the deformation zones, all these things. Right? This is cool, man. I really don't think this one will survive. I could be wrong, but yeah, it's crazy, huh? €8,000 for open data. And actually, to be honest, we all do our contributions here. I mean, we all pay taxes. We all contribute to society here. So, in my view, this data should be free. Like in the United States, every meteorological data that you have there is free. Huh? Radar, lightning, satellite, model data, observations, everything is free in the United States. But you don't have this in Europe here. You'll see that this one will probably die down a little bit, although it has a real interesting feature now. Here, too bad the radars are all a little bit further behind. I don't really see you don't really see a interesting. No, this one will not even reach it. Yeah, indeed. I'm using the open data from the European model for my weather chart. The data that I'm using is the 0.25 currently. Um, but I need to make choices, man. It's either working on the weather models, it's either working on the ChaseBuddy. Um, yeah. Currently, um, my preference is going to the application here, to the ChaseBuddy itself. But yeah, we'll see. We'll see what the future brings. Yeah, indeed, man. We only have so much time. I wish I had more. That's true, man. It's crazy, man. This is just crazy here. Yeah. You can really see like a warm sector here. Like here. Here, this here. You can really see like a warm sector. And if you look closely also, you see something peeping beneath here. going like this. Probably this is cyclogenesis going on here. And I wouldn't be surprised because you have this IPV anomaly here. You have a warm sector here. So probably underneath here, there's going to be a cold conveyor belt popping underneath here, wrapping up in an occluding pattern. Let's see if I can. This is a hypothesis right now. So let's see if we can see that in the models. Let me go to the models here. Hmm. Let's see here if we can see that. Yeah, we do. See here? Starting to occlude here. Around here. See it? See it? IPV anomaly, digging, and then you have here. I'll move this one here. I don't know if you know what I mean, but you have a warm conveyor belt is moving like this. Cold conveyor belt is popping here, where you have this pointy shape here, and you have the dry intrusion here. And this is actually what you already see here. You have this shape here, this the S shape from a moment ago is going to evolve into this occluding shape here. Probably we'll see that also in the MSLP field. I'm going to leave these annotations here. So the MSLP, see? Yeah. See, there's a low forming here, as you can see. So my hypothesis is correct, actually. So over time, as this trough digs further south, cyclogenesis is going to start. We will have a low pressure area over Germany, and probably it will affect you too. If I'm looking forward here, oh no, it won't, because it will be pushed towards the south and southeast. But you already see now that as this trough here digs deeper, right, that cyclogenesis is going to start, which is what you already see it in the ChaseBuddy here as well with the yellow lines here, because this is already the prelude to the formation of a cyclone of an extratropical cyclone. Because here, this is what they call the baroclinic leaf. The baroclinic leaf. Why a leaf? If you do it like this, you actually have a leaf structure, if you know what I mean. Like a leaf of a tree. That's what that's why they call it the baroclinic leaf in satellite meteorology. Yeah. And you already see here notions of the cold conveyor belt popping underneath the warm conveyor belt here, which is kind of nice because you can see this one here, and it already starts to pop underneath it. So cyclogenesis is already underway here. That's kind of cool. And in the warm sector, you have this. We have our thunderstorms here. Let's check a little bit on our thunderstorms now, how they progress. Like these are done. Like here, check it. Check the lightning count. Just plummeted. Here as well. Going to plummet. Let me do the reflectivity again. And as I thought here, thunderstorms are dying here. Here. Why? Because it's already, how to say it, it's already stabilized it, so they can't really they can't really sustain themselves. if you know what I mean. You can see that here, right? Active, and then boom. You'll probably see you'll probably see the same here, right? Because as I have already mentioned, all this precipitation is coming from here. Check it. Like this precipitation field here. So it stabilized this whole region. Whole precipitation field is moving like this, right? If you go further in time. So everything from here to here is already stabilized. This one will also die soon here. This one. Me earlier, and they show a small T-bone in Czechia tomorrow. So a bit of warm sector, and if anything can fire without being messy, that can be interesting. Yeah, indeed. Yeah, yeah. But that's all actually due to this cyclogenesis that's going on. So maybe I haven't checked I haven't checked models in detail yet to see that maybe I don't know if there's some cape or something. I haven't checked. Yeah, there is some cape, maybe. I'm not sure, but we'll see. Yeah, man, I'm really happy how this is turning out here. But all storms are going to die. Are going to die. I think. I'm gonna turn off the radar here for a minute. Like here, this is no longer the same storm. This is a different one here. Like here, also, can we say it's actually the same storm? Let me see. I found an accidental bug in the ChaseBuddy. If I click a radar site, the where and there's a thunderstorm directly above it, or a detection directly above it, both of these things pop up. This cannot happen. I found a bug in my own system. Yeah, as you already mentioned here, they merged. Huh? They merged completely. Huh? And look how destructive it is. I'll probably need to pick another radar here, but just this destructive, man. And here you can see again the how it started to gradually lose its right moving characteristics, like from here, right? You can see it like this. If I go back and forth, you will see it curving along that line. See, starting to lose its right moving characteristics like this. And now it's no more. Kind of cool, right? Here we have an intensification here. I don't know if it has been raining from here to here. Maybe I can't go. I don't know how stable it is here, but as you can see here, this one is still going. Yeah? This one is no longer giving any lightning anymore, which was expected due to the stabilization factor that we've covered earlier. So yes, all these are going to, yeah, it was, they were doomed. It's a shame, but they were doomed. All right. Live on Tropics. I'm going to stop the stream here. I hope you had a wonderful time. Hope you've learned something here. If you haven't, then too bad I wasn't able to give you a good time. Um, Write me something if you what you felt about the stream. What can be improved? What went well? I'm planning to do these more and more in the future, though. Um, but yeah, we'll see how it goes. I hope I can still rename this stream. Ah, yeah, live on Tropics. Yeah, I really learned a bug in my own system. But it's cool to actually start to really work with it now because I've been working on it, but I've not been working with it, if you know what I mean. And right now, I really have the opportunity to do that. So, live on Tropics, thanks for watching. I did not even know that I would have an audience. So, I'm very happy that you sticked around because I was just going to test how streaming works actually. But I'm starting to get a feel of it, how it works. Maybe I'll get better at it probably in the future. I hope so. And yeah, Tropics. See you later, man. Thanks for watching. Have a good night. Have a great weekend. And perhaps later, man. Bye, dude.